um, let you know the train of thoughts in terms of where we've been and where we're going. You guys learn about electron configuration. Okay, so you guys learn about electron configuration. Let me change my pen here. And from the electron configuration, you guys were able to figure out the valence electrons. And why is the valence electron so important? Because when chemistry happens, it's the behavior of the valence electrons that sort of is responsible. So as I was saying, in order to understand polarity, you got to understand electron configuration. That's how the atoms is put together. Then you need to know how the valence electrons play a vital role in chemistry. In fact, if you want to know about chemical reactions, you only need to know about the valence electrons, because it's the valence electrons that make first contact when bonds are formed or bonds are broken. From the valence electron, you guys can come up with the Lewis structure. And remember that the driving force in the Lewis structure is that atoms generally want to have the same number of electrons in its valence shell as a noble gas. So that's the octet rule. Hydrogen just wants two because the closest noble gas is helium. So there are exceptions in terms of the octet rule, but for the most part, atoms combine to form molecules or compounds because they want to either transfer, accept, or share electrons to have the same number of electrons as a noble gas. So that's how we base our Lewis structure. We take the total number of electrons and put it in a pool and then arrange it in such a way that all the atoms are satisfied in terms of the octet rule. From the Lewis structure, you can take a look at the central atom and see how these bonds and these electron pairs are arranged, keeping in mind that it's called the valence shell electron pair repulsion theory. Okay, and that simply means that because electrons are negatively charged, certainly two of them can be found in an orbital. But when an orbital is close to another orbital, it wants to be as far apart as possible. And so the geometry that occurs is by placing these regions of electron density as far apart as possible. Okay? And once you know about the geometry, that is the structure of the chemical, then you can come up with properties. And a critical property that you guys will be able to determine is polarity. And why is polarity so important? Because polarity tells you which chemicals will be comfortable with each other, which chemicals will mix. We hear the term miscible and immiscible, soluble and insoluble, and that goes back to the properties of chemical. So that's where we're going with today's discussion. Okay. Again, if you have any questions, please go ahead and either turn off your mic and let me know, or put something on the chat. So again, remember this table. Make sure you print it out or at least have it in your notes when you are taking the test, because this particular table will help you a lot in terms of figuring out the geometry of a chemical. And the geometry is going to be based on how the valence electrons are arranging. It's going to be linear, trigonal, bent, tetrahedral, pyramidal, or bent tetrahedral. Remember, you need to qualify these two bents either as a trigonal or a tetrahedral, because when you look at molecular geometry, all you're seeing are the atoms, but yet the lone pairs is influencing the internal structure, that is the arrangement by which these atoms are found in their geometry. So this is a good chart to have. And let me just clear this. These are certainly three geometries in which the central atom has lone pairs. Okay, and these chemicals in which a central atom have lone pairs will always be polar. And you will see that shortly when we go through this discussion. Um, so before we go into polarity, let me give you a little background on what I mean by a chemical being polar or non-polar. And probably the best analogy is thinking of magnets. When you think of magnets, you certainly think of a North Pole and a South Pole. And these things basically have um, magnetic orientation so that they're attracted or or they repel each other. Okay, just like planet Earth has a North Pole and South Pole, so does magnets. And so, in terms of the architect of molecules, if you've got two atoms connected, let's say that in this particular case we have hydrogen connected to hydrogen here. Let me see if I can change. Okay, so because the hydrogen atoms are similar in terms of their properties, when they share the bonds, they're going to share those electrons evenly. Okay, so we say that it's covalent because they're sharing their electrons evenly. And so this chemical would be non-polar. There is no separation of charges. On the other hand, when you combine hydrogen with fluorine, fluorine is small, but it also has 9 protons in the center. Okay, um, the 9 protons in the center doesn't necessarily make the atom bigger, but it draws the electron cloud. It draws the electron cloud towards itself. And so what we have is this portion of the molecule is partially um, that symbol right there is the Greek letter delta. I know that you guys know delta as that, but that's capital delta. This is small letter delta. And the delta negative sign tells you that it's partially negative in that end. And the delta positive on that side tells you that it's partially positive on that end. In other words, what's happening is that the electrons are drawn so far towards the what we call electronegative fluorine. That is the fluorine who's stingy for electrons, that the electrons, that this side right here has more electrons, therefore is partially negative. This side over here is has less electrons, and so it's partially positive. The net result is that you have a polar chemical because there's a separation of charge, okay? Just like a magnet. So whenever you see this situation in which the electron cloud is distorted, and that's the key word, when the electron cloud is distorted, so one side is more negative than the other, somewhere in the molecule, then we can say that that particular chemical is polar because now it'll have separation of charges. Okay, so keep that in mind. That's the basis by which we're going to determine whether a chemical is polar or non-polar. So the way we figure that out is that if there's two atoms pulling against each other, then there's no winner in this tug of war analogy. I like to use something that you guys can relate to. That way you can visualize what's going on. So when there's no winner for this tug of war for electrons, then we say it's non-polar. But suppose one atom is stronger than another, or maybe there's a combination of atoms that are drawing that electron cloud towards it, then in this tug of war, there is going to be a distortion. And so because there's a distortion, we say it's polar. But molecules are not only linear, they can also be trigonal or tetrahedral or pyramidal. Okay, so you have to look at the overall geometry. That's why we have to study VSEPR, because if you don't appreciate the geometry, then you don't know whether or not these things, when pulling against each other, are going to cancel out. So in this particular case, if it's trigonal planar and this is perfect 120, then they're going to basically cancel each other out. If you do vector analysis, for those of you who've maybe started calculus, you find out that the net resultant is zero. So again, there's no winner in this tug of war game, and so we say it's nonpolar. On the other hand, as soon as we change the symmetry, so one side is going to have a stronger pull for the electrons. Remember, it's a tug of war for electrons, basically. Then the electron cloud is going to be distorted, and the net resultant or the center will be pushed to one side. There is a distortion on the electron cloud. It's not symmetric anymore, so we say it's polar. And also, if the geometry is such that this particular atom right here doesn't have the leverage that these two have, then the net resultance is going to be in that direction. It's like 2 against 1. And so this particular chemical is polar. And that's why it's critical that you understand the geometry, because the atoms themselves don't dictate polarity. It has to do with the central atom, it has to do with lone pairs, it has to do with the geometry. So let's take a look at water. And the reason why we need to take a look at water is because that's a special chemical. And we will look at water again in the next chapter. But if we remember, oxygen has 6 valence electrons. That's shown right here. Hydrogen has 1 valence electron. When we put the Lewis structure together, then they're going to be sharing electrons. But because of these two lone pairs, the internal structure of the oxygen is tetrahedral. Remember, there are 4 regions of electron density in this case. If there's 4 regions of electron density, then we have tetrahedral electronic geometry. But now 2 of these 4 regions have bonded atoms, and you can see that right here and right here. And because 2 of those regions have bonded atoms, then it's going to be a bent tetrahedral. And that's what you see in this structure right here. Yeah, the lone pairs are there, but they are not counted when you look at the molecular geometry. You're just looking at the atoms. And because the hydrogens are not in a linear fashion, then it's bent. So now we know, let me clear this, that the chemical is bent, and because it's bent and the oxygen has lone pairs, and the oxygen, because it has more protons than the hydrogen, is going to pull that electron cloud to itself. It's much more stingier for electrons, and so what you have is a distortion. And let me try and draw the clouds here. Okay, a distortion of the electron cloud towards the oxygen. And so we say, okay, it's distorted. This chemical is polar. And indeed, water is a polar chemical. And the fact that it's polar gives it special properties that you will see later on in the next section. Okay, so what are the atoms that are stingy for electrons? It's generally small atoms, and small atoms are going to be found on this corner of the periodic table. Remember, it's going to be found on the top, small atoms, because they have fewer shell, and they're going to be found to the right. Why? Because for the same shell, like these fluorine, oxygen, nitrogen, the valence shell is the second shell. So you're not adding layers. So it's not getting bigger, but you are adding protons as you march from nitrogen, oxygen to fluorine. And so it's drawing that electron cloud closer in. And so it's going to have a greater attraction for electrons. And we call that attraction for shared electrons electronegativity. And this is a table of electronegativity. And this table is gives you a visual, okay, of which atoms are the most electronegative. It's generally to the right and to the top. These are your most electronegative elements. We call them electron hogs. And then the large atoms towards the bottom, towards the left, are the least electronegative. And so if you look at the electronegativity table, and you should have a copy of that so you can figure out certain things like the difference in electronegativity, chi. Okay. Then you can figure out whether it's polar or nonpolar. And I'll talk more about this particular difference shortly. But you can see the lowest is 0.7, the highest is 4.0, and the highest belongs to fluorine. Notice that the halogens are not electronegative at all. They don't want to. They don't want more electrons. They're perfectly happy with their octet, helium in this particular case, duet. Okay, it's only these atoms right here that if it gets one more, it has the same number of electrons as the noble gas. So let's move on. So this is a map of how to determine polarity. Okay, and again, the idea is to detect whether or not the cloud, the electron cloud in the molecule is distorted. And I'll walk you guys through this shortly. But the most simplest chemical is a chemical that only has two atoms attached. Those atoms could be different, those atoms could be the same. So it does not have a central atom, because a central atom is going to be an atom that has two or more bonds, or two or more different atoms that are connected to it. Okay, so that's a central atom or central element. So when we have a chemical like CO or O2 or HF, these don't have central atoms, but they certainly are chemicals that we need to address. The way you determine whether it's polar or nonpolar is you look at the difference of electronegativity. Basically, these two atoms are tugging at electrons, and the one with uh, the stronger atom is the one with the higher electronegativity. And then for the rest of these right here, we're looking at the geometry. So let's move on. Okay, let me clear this. So when we have just no central atoms, none, then we have to look at the difference of electronegativity. Okay, and so that difference is based on, again, finding electronegativity table and just subtracting those values. Hydrogen has an electronegativity of about 2.1. So if you've got two hydrogens that are attracted to each other, right, like right here, H2, then the difference in electronegativity is 2.1 minus 2.1, and that's 0. So basically what's going on there is that there's no distortion on the electron cloud, and so we say that that particular chemical is nonpolar. So hydrogen would be right here. The difference in electronegativity is 0. If that difference is between 0 and zero point 0.4, we say that for the most part, the chemical is covalent. For the most part, they're sharing the electrons equally. Now, suppose that difference is between 0.4 and say about 1.8. That's the range. Then we can say that, yeah, they still share electrons, but they don't share electrons equally. So we say it's polar. Remember, polar meaning that there's a distortion on the electron cloud. We say it's polar covalent. They're still sharing, but not equally. And if that difference is 1.8 or greater, then it's not sharing anymore. It's a complete electron transfer. And so we say that that particular bond is ionic. Okay, it's ionic. So remember the rules in naming compounds? We said that there's there's three classification: complete electron transfer, and that would be an ionic, that's electron transfer, unequal sharing, or equal sharing. And that the way we do that, figure that out, is we look at the difference in electronegativity. Okay, so that calculation is pretty easy to do. You just have to find the electronegativity value. So let me go ahead and move, and let me clear this so that you guys can see this. So again, um, how dipole moments work, we call these things the distortion of an electron cloud. Okay, the distortion of an electron cloud, we call that dipoles. And the vector that represent it, we say it's a dipole moment. And if you're a chemistry major and you take PChem, then we recognize that dipole moment as this Greek letter mu, and we can actually do vector analysis. Okay, so here we can say that um, depending on the difference in electronegativity, that dipole moment will be none, will be small, or will be very large. Okay, and this little plus in this end tells you that's the partially positive side, and the arrow points to the partially negative side. Okay, so if we take a look at these right here, these are chemicals. See how even though the carbon, chlorine, excuse me, is polar, well, it's symmetric in both sides. And so even though a portion of the chemical is polar, the whole chemical itself is nonpolar. And the reason why is because when you look at the overall picture, there's no winner in this tug of war game. There is a winner between carbon and chlorine, but you're looking at the entire chemical. And when you look at the entire chemical and you're looking for a distortion on the electron cloud, they're going to negate each other. And that's why you see these symbols right here. One dipole is pointing in one direction, the other dipole is pointing in the opposite but equal direction. The next chemical is water. And we already said that water is polar because oxygen is very electronegative. Then we have hydrochloric acid. Chlorine is much more electronegative than hydrogen. Okay, chlorine has an electronegativity of 3. Hydrogen has an electronegativity of 2.1, and so that difference is 0.9. Okay, and then finally we have a chemical like HF. HF, fluorine, has an electronegativity of 4. Hydrogen has an electronegativity of 2.1, so that difference is 1.9. So that's how you calculate difference in electronegativity. You just figure out what the electronegativity values are, and you subtract one from each other. There is no positive or negative. You take the absolute value. Okay, you take the absolute value. You're just looking at difference. So bond polarity, polar molecules, nonpolar molecules, equal sharing, unequal sharing, complete electron transfer. In fact, the electrons are going from the sodium to the chlorine. So we can see that bond polarity increases from left to right. And why do we call it polar? Well, again, like I said, it's the distortion of the electron cloud, but we can detect polar chemicals. If we put the chemicals in a magnetic field, those things will orientate itself so that the positive plate in electromagnetic field will attract the negative portion of the chemical, and the negative portion of the plate electromagnetic field is going to attract the positive portion. So we can actually detect polar chemicals through experiments. Uh, so here are more examples of that situation. Nonpolar chemicals, of course, are not going to have any bias towards one end or the other. This is a nonpolar situation. This too is a nonpolar situation. But these two certainly are polar. These two right here. This is polar. And this also is polar. One of the things that you will find about in water, because it's polar, is that it can do something called hydrogen bonding. Hydrogen bonding is a property of water such that when it freezes, it maximizes hydrogen bonding. When it maximizes hydrogen bonding, what happens is that there are void spaces in between the molecules. And what that does is that when it goes from a liquid to a solid, is that this void space allows the volume to be greater. Remember the law of conservation of mass? Mass can neither be created or destroyed. It only can be converted from one form to the other. You can convert matter from one form to the other. Well, the number of water molecules can't be eliminated. Okay, you can't just destroy it. The volume, however, is not conserved. Volume can decrease or increase. So we can say that volume doesn't change, does change. But density, you remember, is mass over volume. If the volume gets bigger, okay, and that's what happens to a certain mass of water as it freezes, as the volume gets bigger. And that's why when you put a frozen beverage in the freezer, it looks like it's bloated. And that's because the volume expands. The mass doesn't change, but the volume expands. And so when the volume gets bigger for a solid, then the density gets smaller. And so the density being smaller, like in this particular situation right here, means that ice, the solid form of water, will float because its density is less. Most chemicals are not that way. Most chemicals, as soon as you solidify it, you compact it to a smaller volume. And so if it has a smaller volume, then it's going to have this part on the denominator will get smaller. And so the density will also get um, bigger because the denominator gets smaller. So the density will increase for most solid. And so it will sink in its compared to its liquid form. Anyway, we will be talking about this more later. But again, I want to illustrate to you why we study these things. It's important because then we can explain properties of chemicals. So we've taken care of chemicals that only have two atoms. How about chemicals that have more than two atoms? Okay, so all of these, actually, we're not done yet. All these are examples of binary molecules. They only have two atoms that are attached to each other. Okay, so first thing you need to know whether these chemicals are polar or non-polar is determine their electronegativity value. Notice that hydrogen has a value of 2.1. Chlorine has a value of 3.0, so as nitrogen. Oxygen's 3.5, fluorine is 4.0. Iron here is 1.8. Sulfur is, sorry, that's silicon. Sulfur is 2.5. That difference is 0.6. And why is that important? Because you guys can do this calculation, okay? And then you can put these in the order of increasing polarity, okay? And the range will go between, say, 0 all the way up here to about 2.3. I apologize for my PowerPoint. I think that the format got lost in the translation here. But you can see that fluorine is going to be 0, so it's completely covalent. Hydrogen also is 0. NO, the difference between nitrogen and oxygen, nitrogen is 3.0, oxygen is 3.5, so that difference is 0.5. It actually should be right here, okay? Then as we continue on, copper sulfide is a little bit more polar, and then hydrobromic acid is a little bit more polar. So from this point on, we have chemicals that are polar covalent. What other chemicals are polar covalent? Iron sulfide. Just calculate the electronegativity. Carbon monoxide. Oxygen's 3.5, carbon's 2.0. That difference is 1.0. It actually needs to be put right there. Hydrofluoric acid, that's 1.9. Hydrogen's 2.1, fluorine's 4.0. Then we get to the ionic substance, sodium chloride, magnesium oxide. So what we have here is that these chemicals, just based on electronegativity, is covalent. These chemicals are polar covalent, and there's a lot of them. And then finally we get to ionic. Why is there a 2 before the 1.9? Yeah, that's because my formatting, when I converted my PowerPoint to my iPad, didn't work, okay? So that's the reason why it didn't work. If you go back to my original PowerPoint, you see that the scale is correct, but in this particular case, the formatting messes up when you put it in a different computer, okay? So that's the reason why these numbers here, and I put these numbers here, got messed up. So let's move on. I was just a technical difficulties in terms of translating my PowerPoint from my computer to the PowerPoint in my iPad. Let's take a look at these chemicals. Now we're looking at chemicals. Well, not so much this, but the rest of these in which there are a central atom. This is a central atom. This is a central atom. So is this. We've got two central atoms here. This is a central atom. These also are central atoms. This is a central atom. This is a central atom, central atom, central atom, central atom, central atom. These two are central atoms. Okay. So why is this important? Because again, it's the central atoms that determines the molecular shape. And these are all Lewis structure. These are all Lewis structure, which you guys should know how to do. And again, if you try and do the guesstimate, that is just play electron gymnastics by trying to figure out where the electrons go to satisfy the octet rule, it may take you a while. Use the bond table that I showed you last time, because that makes things a lot easier and it expedites things. You just need to practice it. Once you understand how that bond table works, it'll go faster than if you were trying to guess how those electrons are arranged. So the bond table, there's a reason why I use it. It's because it gives you consistency. And remember, it only works for those chemicals that obeys the octet rule. So let's look at some of these chemicals right here and make a note. That central atom right there, let me change my pen, has a lone pair. Automatically, I know that that's polar. I don't even have to do the analysis, okay? These central atoms right here have lone pairs. I already know that that's polar. These, even though only one of them has lone pairs, the fact that any of the central atom has lone pairs, I know that it's going to be polar. Okay, so if you know the Lewis structure and you lay it out and you investigate the central atoms and any of the central atom has lone pairs, it has to be a central atom now. Okay, not terminal atoms, not terminal atoms like these. That doesn't count. It has to be central, because the central atom will automatically tweak the geometry. So this looks linear. It's not linear because of that lone pair. That's what the lone pair does. Any molecule that has lone pairs on a central atom will automatically be polar. The other feature I want to point out is look at the terminal atoms. The terminal atoms are what comes at the end. You see how these terminal atoms right here are identical? Well, that means that this chemical is perfectly symmetric. And so if it's perfectly symmetric, there's no distortion on the electron cloud. And so we can say it's nonpolar. See how these two terminal atoms are the same? Even though they have lone pairs, they're identical. We can say it's nonpolar. Okay. Likewise here, even though these two are the same, but these two are the same right here, but they have lone pairs. That doesn't matter. The fact that they're identical makes this chemical symmetric, so we say it's nonpolar. This chemical right here, however, have different terminals. So the symmetry is broken. If the symmetry is broken, it becomes polar. So those are just quick visual of how to determine whether a chemical is polar or nonpolar. First, you want to make sure that you have central atoms. You got to make sure that the central atoms doesn't have lone pairs. If it has lone pairs, it's automatically polar. Then you look at the terminal atoms and make sure that they're symmetric. If they're not symmetric, then it's also polar. Basically, you're looking at symmetry and you're looking for distortion due to symmetry. So let's go through this flowchart and it'll make more sense in terms of the organization and what we just talked about. How many central atoms? If there's only two, then we're just looking at the difference in electronegativity. Okay, and that'll determine whether the chemical is polar or nonpolar. If there is, and these are the examples, carbon monoxide and oxygen. Oxygen is a nonpolar chemical because they have equal attraction for bonded electrons. Carbon monoxide is not a polar chemical. It's polar covalent. If your molecule has a central atom, only one central atom, are there lone pairs? Are there lone pairs on the central atom? If the answer is yes, then it's polar. Like ozone. Ozone is this chemical right here. Notice the central atom has a lone pair. It's polar. If there are no lone pairs on the central atoms, then you look at the terminal atoms, and that's at the end. That's what's sitting in at the edge. Okay, are all the terminal atoms the same? If they are not the same, then it's polar, because you break the symmetry. If they are the same, and this is an example, this chemical is this right here. Notice that the terminal atoms are not the same. It's automatically polar. The symmetry is broken. If they are the same, then it's nonpolar. And carbon dioxide is this right here. If there are more than one central atom, so we're getting to more complicated species, are there lone pairs in any of the central atoms? Any. If the answer is yes, then it's automatically polar. If the answer is no, like hydrogen peroxide, I think I showed you that structure. Hydrogen peroxide is this. And it looks nonpolar here, but that's because I'm drawing it in a two-dimensional surface. It actually is polar because the skeleton around that oxygen is tetrahedral. So the geometry around that oxygen is bent tetrahedral, likewise for the other oxygen. It's a polar chemical. If all the central atoms, if there are no lone pairs on the central atoms, then you have to look at the terminal atoms. And if they are identical, all terminal atoms are the same. If they're not the same, then are all terminal atoms the same? No, then it's nonpolar. An example of that would be this. Okay, if you take a look at that chemical, the terminal here is chlorine, the terminal here is hydrogen. So it's nonpolar. You've broken the symmetry. But if all terminal atoms are different, or there's a different, sorry, if all terminal atoms are the same, yes, then it's nonpolar. And that's an example right there. Let me go back to this part of the flow chart. Are all central atoms the same? No, it's automatically polar. So you can see, just based on this organization, we can now classify each one of these as polar or nonpolar. That is polar. It's got lone pair on a central atom. That's polar. The terminal atoms are not the same. This is nonpolar. No lone pairs on the central atoms. Terminal atoms are identical. This is nonpolar. Central atoms do not have lone pairs. Terminal atoms are identical. This is also nonpolar. Central atoms doesn't have a lone pair. Terminal atoms are identical. This is polar. This has difference in the terminal atoms. This is nonpolar. All terminal atoms are identical. This is polar. Terminal atoms are not the same, plus a lone pair has a central atom has lone pairs. This is polar. Terminal atoms are not identical. And of course, this is also polar. So just by visually inspecting the chemical, that's why molecular geometry is so important, and the Lewis structure, you can determine whether the chemical is polar or nonpolar. Okay. And this is just a summary of which chemicals are polar. That's shaded in red. And which chemicals are nonpolar. That's shaded in blue. So examples, of course, are beryllium hydride. This is a linear chemical. This is one of the chemical that is an exception to an octet rule. It's only got 4 electrons in its valence. This chemical is nonpolar. BH3, this chemical is perfectly symmetric. Again, this is an exception to the octet rule. This chemical is perfectly nonpolar. So is CH4, but NH3 is polar. And the reason why NH3 is polar is because if you do the Lewis structure, you have this. You see how this nitrogen has a lone pair? It's automatically polar. So this is just an exercise if we were in class where we would break out and you guys would figure out whether the chemical is polar or nonpolar. Okay, you should try this on your own because definitely you guys are going to be seeing a question like this in your next test. So that pretty much is it. Let me go back to that. The key to determine polarity is you work on the Lewis structure, you know the molecular geometry, and then you use common sense to determine whether there's a net distortion. That's the key of the electron cloud. And that net distortion can originate from lone pairs on the central atom, any central atoms, and difference in terminal atoms. So if the terminal atoms are different from each other, then what you have is a distortion of the electron cloud. So I hope that's clear in terms of what we just talked about, okay? In terms of figuring out properties. Because we're gonna use this knowledge of polarity to talk about properties such as boiling point, melting point, vapor pressure, okay, viscosity. All properties that we can measure for matter. And that's the next section that we're going to be looking at. So we're going from chapter 10 to chapter 12.